Hi everyone, and welcome to the third of 4 videos going through some past exam questions on transition metals and complex ions. The first question we've got here is kind of similar to one we saw in one of the previous videos. It's telling us we've got iron, copper and platinum are examples of transition elements. It wants us to define what we mean by transition element and show that iron fits this definition using full electron configurations of iron as the element and in its common oxidation states. So it's quite nice. I do like a question that tells us exactly what they want. Okay, it's pretty clear here what we're going to need to do to get the mark. So we need the definition of a transition element. So this is just one we need to remember. Okay, a transition element forms at least one ion with a partially filled d subshell. And remember that we talked about that importance of it being an ion, not the element itself, an ion. And then it says, show that iron fits this definition by using full electron configurations of iron as the element and its common oxidation states. Okay, so iron, the element itself, its electron configuration has, let's see, where's iron? We go through all of this and we get to 4s2, 3d, 1, 2, 3, 4, 5, 6. Okay. And again, if you've watched the previous videos, I said I would always write this out properly. I wouldn't do the shortcut with having a noble gas. First, I'd write the full electron configuration just to be on the safe side. That's what they're testing, right? They're going to want to see if you can do it properly. So we said it'd be 4s2, 3d6. And in its common oxidation state, so again, we kind of just need to know what those are. Iron commonly makes Fe2+, and it also makes Fe3+. Okay. So Fe2+ is going to have lost 2 electrons from here, and the 2 electrons that it's going to lose are going to be the 2 4s electrons. 3p6, get rid of those, and it'll still be 3d6. And then Fe3+ is going to have lost 1 extra electron compared to that, so that's just going to go down to 3d5. And that should be it. It's a 4-mark question, right? That's going to be our 4 marks. Define transition element, give the full electron ion as its element and as its common oxidation states. That's it. Okay, so that's quite a nice question there, I think. Okay, moving on. We have this ammonium hexachloroplatinate. Okay, is a complex of platinum used in platinum plating. Okay, it contains the hexachloroplatinate ion. Okay. Draw a 3D diagram to show the shape of a hexachloroplatinate ion. Show the charge and the value of the bond angle. Again, so this is a nice question. 3 marks, we know exactly what we're going to do. We did show the shape, the charge, and the bond angle. That's where we're going to get 3 marks from. Okay. Anything with hexa, we've got 6 ligands going on here. So that tells us there's going to be 6 ligands, and if there's 6 ligands, it's going to be octahedral. And again, if you've watched the previous videos, you'll have seen this. It's always is the same shape, right? We've got our platinum in the middle, and then an octahedral shape means you've got ligands above and below. You've got 2 going into the paper, which we represent with the dashed bonds, and you've got 2 coming out towards you, which we represent with the wedges. Okay, so you draw that octahedral shape. Then we just put the ligands on. Okay. Hexachloroplatinate is going to be platinum and 6 chlorines, isn't it? This is straightforward. We're not worrying about the ammonias here. So that's that. So that's showing the shape. We need to show the charge on the ion. So this needs to be in brackets. It's going to have a charge. So what's going on here? Contains the hexachloroplatinate ion. So we know that the 6 chlorine ligands, so 6 lots of Cl minus is going to be 6 minus. But then how are we supposed to know what the platinum is? Like, this is a bit of a tricky one, because it's going to depend on what oxidation state platinum is in. But this is where the 2 ammonias are giving us a clue, right? Although that's not part of this complex, it's then bonded to 2 ammonias. We know that NH4 plus is the ion here. Okay, and if we've got 2 of those, that's going to be 2 plus charge. Okay, so if that's got a 2+ charge from those two, that means that this complex overall must have a charge of 2-. Okay, and that's why they're bonding together. Okay. And then finally, we need to have the value of the bond angle. So let's put this on here. And this again is just something that we need to know. In an octahedral complex, the bond angle is 90 degrees. Okay, that's just a fact that you want to remember. Okay. Okay, if we move on, this question carries on. So it then talks about this thing, which is oxaliplatin. So it's a different complex of platinum used in cancer treatment. You might be seeing a bit of a link here that these sort of platinum complexes are often used for this. So a molecule of oxaliplatin has a square planar shape, okay, again, that we've seen before, platinum. It's got 2 bidentate ligands, okay, the structure is there. What is meant by a bidentate ligand? Okay, so a bidentate ligand, you can see from the diagram, is forming 2 bonds. So it forms 2 coordinate bonds to a transition metal ion by donating 2 lone pairs of electrons. Okay. Right, and then finally it wants us to show the structures of the 2 bidentate ligands. So this is a nice easy one really. We're just going to copy it out from the diagram that we've got here. So we're just going to split this here, right? There's one ligand this side and here's the other ligand this side. Okay, so we can just copy this out. We've got this hexagonal ring here, and then we've got NH2. I'm just going to copy this exactly as it is. And that's it. Here's a lone pair on the nitrogen, right? So that's going to be that one. And then over here we can copy this. But this is where we need to be a little bit careful. This is going to make, again, we're going to have lone pairs on the oxygens here. But oxygen only forming 1 bond is not normal. Oxygen wants to make 2 bonds, and this is going to have to be an ion. This is going to be negatively charged on those 2 oxygens. Okay, the nitrogen isn't, because nitrogen's got 2 bonds to the hydrogens and 1 here. Nitrogen having 3 bonds and a lone pair is what we're used to, isn't it? So this is a neutral ligand. This ligand is a 2- ion. Okay, and you might come across these, they're fairly common ligands. This is similar to a bidentate ligand that we saw in a previous video. It just didn't have this extra ring on it. Okay, this ethane diamine is a fairly common ligand. They've just decided to bung an extra carbon chain on there to make a ring out of it. And this dicarboxylate ion is a fairly common one. This is from ethane dioic acid. It's one of the more common bidentate ligands that does come up quite a bit. So if you practice more of these sort of questions, you might see this ligand coming up again. And hopefully that will help you get a bit more familiar with it rather than kind of looking and going, what the hell is this? Look out for that one because it does come up quite a bit.